one final example of variation of parameters is going to be our 4y double prime minus 4y prime plus y is equal to e to the x over 2 root 1 minus x squared. Complementary solution, just like we've done countless times at this point. 4m squared minus 4m plus 1 equals 0. Factoring, I think this is another one of those double roots, so we get 2m minus 1 quantity squared. And if we go through and solve it, m1 equals m2 equals 1/2. All right, so, and there is some good news, because if you look at the function, and then let's take a look at what the complementary solution is going to look like. So we're going to have c1e to the 1/2 x plus c2x e to the 1/2 x. Notice that we have an x to the 1/2, or I'm sorry, an e to the 1/2 x in each of those. So we're hoping that when we start multiplying those w's out, that some of that stuff is going to simplify really nicely to maybe an e to the x or something like that. So anyhow, we define y1 to be e to the x over 2, or 1/2 x. Okay, so that's right here. And then y2 is going to be the x e to the x over 2. And we know, unfortunately, that y of x is e to the x over 2, square root 1 minus x squared. All right. So now we need to find all the w's. And you can tell with how much enthusiasm I said that I'm ready to do it. So w is going to be equal to y1, which is e to the x over 2, the derivative 1/2 e to the x over 2 by chain rule, y2 x e to the x over 2, and unfortunately product rule, so we're going to get an e to the x over 2 plus 1/2 x e to the x over 2. Chain rule, product rule. Cross down, cross up. Hopefully something cancels out. So when we cross down, e to the x over 2 times e to the x over 2, if we add x over 2 and x over 2, that gives us 2x over 2, or just x. So we're going to get an e to the x plus 1/2 x e to the x minus 1/2 x e to the x. And mercifully, almost magically, we're left with an e to the x. Thank goodness. Right, w1. 0, f of x, y2, y prime 2. 0, e to the x over 2, root 1 minus x squared. X e to the x over 2, and the derivative doesn't even matter, because when we multiply down we get 0, and then when we multiply up we're going to get a pretty ugly term there, so we end up with 0 minus x e to the x root 1 minus x squared. Hopefully we don't have to integrate that. I don't think we will. I think it'll turn out pretty nice. Finally, w2. Same thing, except we're going to switch the columns. So y1, y prime 1, 0, f of x. Remember, y1 was e to the x over 2. It doesn't matter about what the derivative is, because we're going to be multiplying that by 0. And then our function, e to the x over 2, square root 1 minus x squared. Alright, and when we cross that, that's going to give us e to the x square root 1 minus x squared dx. Or not dx, excuse me, minus 0. I was getting ready to integrate it. Alright, So now we can find u prime 1, and then unfortunately u prime 2, and you'll see what I mean by unfortunately. So u prime 1, remember that's w1 over w. W1 we found to be x e to the x, or negative x e to the x over 1 minus x squared. And remember w all the way back we found to be e to the x. This works out really nicely. X root 1 minus x squared. All right, u prime 2. Not so nice. I'll show you why in a moment. So remember, u prime 2 was simply e to the x root 1 minus x squared divided by e to the x. And I know several of you are thinking, oh, okay, well that only leaves us with 1 minus x squared. That's much nicer than negative x 1 minus x squared. So you think, until we start to integrate it. Now, we do have to integrate each of those. Let's just go ahead and integrate now, and then we can throw it back into the formula for the particular solution. Let's start with the easy one. Negative x root 1 minus x squared dx. Clearly this is a u substitution. So we're going to say u is equal to 1 minus x squared du. Derivative of 1 is 0. Derivative of negative x squared, negative 2x dx. We like the x, we like the negative, and we like the dx. We just don't like the 2. So let's just divide by 2, and we're left with negative x dx. So when we substitute, we're going to get the integral of du over 2, and then square root of u, or u to the 1/2. All right, so remember, this is the same thing as square root of u. Right. Very easy for us to evaluate. This is now going to be 1/2 u to the 3/2 divided by 3/2. We can multiply by the reciprocal of the denominator, so it'll be 2/3 times 1/2 is 1/3. And remember we said that u was 1 minus x squared to the 3/2 power. So we're going to hold on to that, because unfortunately now we got business. We've got to evaluate this. All right. A few options. One, we could quit. 2, we could throw it in the computer algebra system and not get any credit for that part. Or 3, we could go ahead and evaluate it using the trigonometric substitution. One of our least favorite, if not our least favorite method of integration, because it is lengthy. All right, so we're going to let x be equal to sine of theta. Remember, there's 3 choices: sine, secant, tangent. If it's a minus x squared, then it's just going to wind up being our a sine of theta. Dx is cos theta d theta. Remember, sine is the same thing as x over 1. It should also be noted that the arc sine of x is theta, just by taking the arc sine of both sides of this expression. All right, that's going to be useful, I believe, at the end of the problem. All right, and then finally, I don't know why it keeps going back up there. We're going to draw our triangle. Sine is opposite over hypotenuse. So 1, opposite is x, and then square root of 1 minus x squared by our Pythagorean theorem to be able to complete the triangle. All right, so now we can substitute, unfortunately. So now we get the integral of 1 minus, we're going to replace x squared with sine squared theta. We're going to replace dx with cos theta d theta. All right, so there is some good news. 1 minus sine squared is cosine of theta. squared. So now we end up with the integral of the square root of cos square theta cos theta d theta. Out of room. Does that mean we get to quit? No. Go all the way back up. Got to find some room here. All right. Just making sure we have enough room. All right, so we're at this stage. Well, we were at that stage. It's gone. I'll just rewrite it. So we were at the point where we had the integral of the square root of cos square theta cos theta d theta. That's going to be now the integral. So this just turns into cos theta by taking the square root. Cos times cos is cos square theta d theta. So that's good news in the respect that we can actually evaluate that. Now we've seen this type of integral before, and remember, or maybe you don't remember, the one thing I said don't do is just to add 1 and divide by the new exponent. That is not correct. That only works for polynomial. You might remember that we have to use the power reducing formula. And we saw the power reducing formula earlier. For cosine squared, that is 1/2 plus 1/2 cos of 2 theta. All right, so at this point, we are going to integrate, finally, at least for this one. There's a d theta out here, excuse me. So we're going to have antiderivative of 1/2 is just going to be theta, 1/2, plus the antiderivative of cos 2 theta is going to be 1/2 sine. We also have the half from out front. So remember, it's the reverse of the chain rule, so we divide by the exponent. So this is 1/2 sine 2 theta. All right, so now here's where it gets really fun. We can't go back to the triangle yet. Okay, so usually what we do is we go back to our triangle. I think I deleted the triangle all the way down here. That's fine, I'll redraw it really quickly. So remember, we had this triangle. We had 1, we had x, and we had 1 minus x squared, and we had theta. We can't substitute yet. And also remember that we had this substitution. We had x equal sine theta, and we also had that arc sine x equals theta. And the reason we can't back substitute is because the triangle is only for theta, not 2 theta. So we have to use one more trig identity. You might remember this one, that sine of 2 theta is a double angle, and that can be written as 1/4 times 2 sine theta cos theta. All right, so pulling out all the stops of trigonometry as we go along here. Boy, this question could just be a final examination. All right, at this point we're going to simplify. We're going to back substitute, so we get 1/2 theta plus 1/2 sine theta cos theta. And mercifully, we're going to back substitute in terms of x. Remember, theta is arc sine x, so 1/2 arc sine theta plus 1/2 sine of theta. Remember, sine is opposite over hypotenuse, so that's x over 1. And then cosine is adjacent over hypotenuse, so that's 1 minus x squared over 1. All right. And so finally, I think this was u sub 2, about 5 minutes ago. And we can clean up u2 to be equal to 1/2 arc cos, or arc sine, excuse me, of x. This should be an x, not a theta, excuse me. plus 1/2 x root 1 minus x squared. All right, and that's U2, I hope. Let's go back up just to make sure. I can't remember which one was U2 and U1. I might have deleted it. All right, that's fine. Yep, U prime of 2. So this was actually U1. All right. Good thing I checked. And good thing it was still there. All right. So let's get to our final solution. So y of x. So we're going to start with the y1 and y1 a long time ago, literally about 15 minutes ago, was e to the x over 2, and y2 was x e to the x over 2. So we have e to the x over 2 times u sub 1, which is 1/2 arc sine of x, plus 1/2 x root 1 minus x squared, plus x e to the x over 2. And a while ago, I think we got like a 1/3 of the natural log, or I'm sorry, it was not natural log. It was 1 minus x squared to the 3/2. Okay, I'm pretty sure that's what it was a while ago. Let me scroll up, see if we still have that one. No, I think I deleted it. Even if I scroll down, I think I deleted it. Yep, that's okay. I'm pretty certain that's the answer. All right. Plus, we had the original yc, which was c1 e to the x plus c2x e to the x. Maybe that was x over 2. I'm pretty sure it was. All right, I'm going to leave it like that because once we start going past 20 minutes in our video, that just seems like it's an unnecessary problem, although you might feel like this is unnecessary. All right, so now we have, fortunately or unfortunately, seen all the different ways that we can analytically solve these types of second-order differentials, both by using variation of parameters as well as the undetermined coefficients method. I'm going to post one more video in this section, but it's not necessarily going to be on how to do things analytically. I'm going to show you how to use Wolfram Alpha to verify your answers. All right, so that'll be our last video, which won't take too long. So sit tight for that one. I'm sure it's going to be exciting.